you just do it, it'll turn out okay. And welcome to the first episode of our currently 5-part miniseries, Before the Earth. Well, we talk about the structure of the universe, what happened in the 10 billion years before before the Earth decided to crunch together rocks and become a sphere. With me are three guests today. From the bottom, starting with the bottom left, introduce yourselves.
Okay, I guess I'm the bottom left. Hello. My name is Landon Knoll. I'm an astronomer. And as they say, good morning, good afternoon, or good evening, depending on your time zone and latitude, because those two things matter. And I hope you're doing well, and I hope you enjoy this exploration of what I consider our favorite universe.
Awesome. Yeah. Hi. I'm Tapioca Weasel. I also go by Vandy. I'm an atomic physicist, so I'm not an astronomer or anything. And yeah, I'm just here to get the opportunity to ask Landon a lot of questions.
Oh, hello. I go by the name of Nes20, but you can call me Nes for short. And I'm here to be. I will be happy to hear or to learn about the earliest instances of the cosmos. Very curious.
All right, and with that out of the way, Landon, start your introduction.
So the big topic of this thing is the Big Bang model, and by the way, you're talking about atomic physics. We'll be doing a bunch of the atomic physics stuff in BE1, which we're going to talk about some of the early fractions of a second, things that we can somewhat simulate in accelerators, but somewhat are beyond our reach. BE2 is going to be talking about the first sort of million years or so, depending on how much time we have, pun intended, of the Big Bang process. And BE3 is going to be formation of those large structures of the universe with galaxies and star evolution. And BE4 is going to be talking more specifically about formation of solar systems. I'm a planetary scientist, so I get excited about planets mostly, but that's just my topic. But we're going to talk about the Big Bang model, and I'm going to try to use language carefully. I have Feynman in the background who would yell at me if I'm using terms which are he would call cringe worthy, right? So one of the things in particular, what is the Big Bang model? It's a model that the universe started in or the early universe, I should say, not started, but that the universe early on was in a hot, dense state, and it changed from that, and that the Big Bang model is part of the change even to the present day. The Big Bang is a model. I know that's it's not the show. In fact, the Big Bang theory, I think, is probably a misnomer, but that's a
not to be confused with the TV series.
Yeah, so it's not the show, it's not the K-pop thing. We're talking about it's a model that the astronomers, the people in cosmology, know about how the universe is transforming. And one thing in particular is that the Big Bang model does not describe the cause of the Big Bang process. It does not really even address what might have happened before the Big Bang model started, even if it's reasonable to even talk about before. The other thing is that the Big Bang model is the term Big Bang was a term used by astronomer named Hoyle, who was a proponent of the competing model at the time, the steady state model of the universe, and he did it on a radio show. And he called the other model, the big model, Big Bang, as a pejorative, but the name was kind of catchy and stuck, and it's there. It probably is not the best name for the model, right? I like what Dr. Tyson calls it, he says the main event, right? Think about the Big Bang model as the main event of the cosmos. It's important also to know that the Big Bang is not an explosion. It's not a point in time. It's not a place, right? It's a process. And the fundamental thing, and this started off with a physicist named Lemaitre, who, using what was around 1927, using Einstein's field equations, looked and applied Einstein's general relativity to the cosmos, and the equations, what the equations imply, and along with something Hubble had observed, which is that the universe was expanding. And Hubble had used various people's observations as well as his own to kind of show that the universe was expanding. And Lemaitre came up with a model that says, if the universe is expanding, if you run it backwards, run the film backwards, the universe must have at some point been a very hot, dense, in a hot, dense state. And if that's the case, how did it get from a hot, dense state to now? And that's the Big Bang model. It's a process. It's important also to understand that it's not an explosion. The Big Bang is space.
Right, where you said a lot of people, especially let's call them creationists, call it explosions and make fun of that. Have you ever had to deal with YECers about your subject?
Yeah, so though it's not very interesting, and it's sort of like, if someone came in and said, my view of chemistry is there's 4 elements, and earth, fire, water, air, and that's it.
Mhm.
And ethers, and I would say, well, that's a nice thing, but I'm not interested, right? and so that's usually the Big Bang model has an enormous amount of evidence supporting it. It's not just some wild ass thing that someone pulled out of their rear. It has enormous amounts of observation and data and experiments to back it up. And in fact, there are very good reasons why the steady state model was discarded. Steady state was this notion that the universe is infinite, it's been there all the time, all the place, and at steady state people, when we found the space was expanding, they sort of said, well, what's happening is matter is being constantly created so that the universe is basically filling in these spots. And this is obviously not what's happening now, which is one of the reasons why the Big Bang model was adopted, as sort of became preeminent because of experiments and observations backing it up.
Like, one of the best analogies that I have seen is like somebody grabbing a balloon and drawing with a pencil or like or something like drawing dots on the balloon, and then blowing the balloon up, and you see that every single dot is like moving away from each other at equal distance, and that's basically the analogy of what happens with the Big Bang. It's not like the balloon is not exploding; it's just expanding. Yeah. Of course, the rate of expansion is different at different times.
Yeah, and that's a good. There's some good things on that analogy. Of course, one thing we always have to be careful of is analogies are give you hints of what happened. They're not the thing. And so one of the things in particular is that the in the Big Bang model, space, if you will, the grid of space-time, is undergoing expansion. But other things in particular is that if you were to pick some point in the Big Bang model, you have a horizon that you can observe. We're assuming that Einstein's hypotheses are correct, and that no information can transmit faster than c. So if you start observing, probably 1 second, you have 1 light second of stuff that you can interact with, right? Your observation your observable universe gets bigger as time goes on because of the way space-time works. So here's I think is a key point. The universe underwent change, and one of the things that because Metroid says the universe is expanding. So the grid, think about the graph paper, the grid of space is expanding. Like if you have, take out a rubber ruler, right? And a rubber ruler meter long, because we're not metrically challenged here. A meter long ruler, that's rubber, right? And if you stretch it to be twice as big, the 1 millimeter marks are now 2 millimeters wide because you stretched it. And the 1 centimeter marks are now 2 centimeters, and the 10 centimeters are now 20 centimeters. Everything, in fact, the farther you go down that rubber ruler, the faster that mark is moving away when it's doubling. That's just what we talk about, the space expanding. Galaxies and things in it, which we'll talk about in BE 3, I believe, are really kind of staying put respect to the grid of space. Effectively, I mean, they're gravitationally orbiting each other, but effectively for the large scale universe, they're saying they're going along for the ride as the grid of space is expanding. The Big Bang models is really the implications of what happens when the grid of space is expanding in weird ways and expanding in unexpected ways. But again, Lemaitre said Einstein's field equations and Hubble's observations based on other people's data and his own, that the universe is expanding. And if you run that movie backwards, it must have been the case that the universe was in a very hot, dense state. And this is really what the Big Bang model probably. It doesn't say how that came to be. It doesn't talk about before that process might have started, even if it's reasonable to even ask that question. It's about the process, the going forward. And it made predictions. The model made predictions, which have been borne out in countless experiments, both in high energy physics and in observations. So it's a well supported model, but it's how the universe evolved. Now, I'm not talking about evolution as in biological evolution. I'm talking about how the universe went from a hot state.
Yes. So to those people who say this is one of the 6 evolution things, you're wrong. It's not.
Yeah, it's a thing. Like I'm more of a biology person, and like many evolutionary biologists get like they get annoyed when somebody is using the word evolution to mean change or something else. Of course, I won't. I'm not a. I won't complain like that if somebody else is using a word in a different way than I'm used to.
Yeah. Evolve is a perfectly good English word.
Yeah.
And it has meaning. Yeah. And in biology, it's been extraordinarily well established about the modern theory of evolution in biological systems, right? And I'm not a biologist, but for you like you, I do deference to your experience in that process. As a planetary scientist, I'm interested in how the universe ends up forming planets, for which interesting chemistry starts, the physics and stuff, and at that point, I let biology and biologists carry this stuff forward. And a lot of my career in astronomy has been about trying to understand that process, trying to understand the Big Bang model and what it means for planets, and that understanding has evolved. Get used to the word. Right?
So, real fast,
sure.
We're on this topic. Now, this is a full-blown theory, not a hypothesis or fact or guess or anything like that. It's at this point, the Big Bang is a full theory.
Yeah, it is a physical theory. And so, I guess, and you understand theory, we're using it in the scientific term. We're not using it in the it's a vague guess, right? Theory is something which is the highest level that you can achieve in science, of something which is falsifiable, something which has been demonstrated time and time again by observations, made predictions. Those predictions have found to be reasonably correct. The model evolves as well as we understand more details. Everything about the model is not known. There are parts that we're still learning about, we're discovering, right? Everything is
like that. There's also like many people also don't realize that many things that even they would accept as common knowledge, like for example, that you have also atomic theory. The idea of atoms are a theory too, and also germ theory of disease. Although, of course, there are always those few people who even deny those things, unfortunately, as well. But
yeah.
Aside from that, theory in science is very different from what common, like in the common vernacular, how it's used.
Yeah.
And we'll get to that history in a minute. But before we move on to the next topic, anything you two have any other discussions, questions about the process of the Big Bang? Before we move on?
So when I talk about it with people, and some of the questions I've had myself in the past have been, if everything is expanding, if space itself is getting bigger, I don't really know how else to ask it other than, how do you know? Because doesn't everything just sort of scale? Like,
yeah. So there's a couple of things, and this is back to talking about, unfortunately, some of the misconceptions of the Big Bang model.
Because it's not true that everything does get bigger like that.
The easiest or more concise way to talk about it is looking at field equations and so forth, but those are hard to converse about. So we have to jump into analogies. Understand the analogies, like the balloon analogy has limitations, right? So the universe is not a surface of a balloon, right? An example, but it's a good analogy. The universe is not a rubber balloon. So one of the things that is that the Big Bang model assumes that the Big Bang process, one way is to say, one version of the model is that the Big Bang process established space-time. Now, I use the word space-time, not space and time, but space-time. Space-time is a very specific thing developed in relativity theory, which is that space and time are kind of intertwined. They're not separate things. And that the space, if you think about the grid of space over time, changes. Now, one of the things in particular is it's not, the Big Bang is not an explosion in one spot, right? Because along that stretching rubber ruler or a dot on the expanding balloon, there's an origin. Everything is moving from everything else. But the dot on the ruler or the mark or the dot on the balloon doesn't move, right? It stays the same relative to the grid of space. And it's if you will, the graph paper is expanding. If you think about 4-dimensional graph paper.
So if I understand correctly, if you had two small, almost massless, but if they were actually massless, they'd have to be traveling at the speed of light. Mm-hmm. But if you had two small test masses very, 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 very far away from each other in a totally empty region of space that is expanding like the universe is expanding, those two objects could initially start and have some distance that you could measure, for example, with an actual physical ruler. And then 1 million years later, if you measured it again with that same physical ruler, you would need more of the rulers.
Yeah, you need more grid space, right?
Exactly. Your ruler has not gotten bigger.
Yes.
It's the separation between those points has gotten bigger, which is why they had to be very small enough to not be gravitationally bound in this example.
And And so another thing to consider is that it's an expansion of space, in that but one of the implications is that like galaxies, right? Let's ignore let's talk about cluster galaxies. Right? Cluster galaxies is orbiting each other, and for all practical purposes, they're just sort of orbiting around a center of mass, spinning around each other. That spot tends to stay in place unless there's some force causing it to move through the cosmos. It tends to be relatively stationary, and it's the grid between galaxies and galaxy clusters, more in particular, that is expanding. Like there's actually it's like adding more tick marks between them.
Yeah.
One of the implications is, and here again, you have to be careful when you hear astronomers saying, here is a quasar, and this quasar is 12 billion light years, right? What they're really saying, if they're being pedantically correct, is 12 billion years ago, when light that we're seeing in our now left, the scale of the universe was such that it took 12 billion years for those photons traveling at effectively c to reach us. That's what he means by saying something is 12 billion light years away. Right? Now, in that intervening 12 billion years, the Big Bang process continues, and there's now more tick marks between here and there. Right? The photons eventually reach us after 12 billion years, because when they left that quasar, the scale of the universe was such that it took 12 billion years to reach us. If we take a mirror and reflect those photons and go backwards, a couple things might happen. Is that first of all, if those photons ever reach that spot, it'll take a lot longer than 12 billion years. Why? Because the universe is expanding. In fact, it may be that those photons never get back. Right? There appeared with observation, there are things we can see now in our now that light left in back then reached us that we can never reach again, because as the universe, one of the things that this universe expansion is accelerating, the light will never catch up. That it's going to be more space between here and there than light can travel, and so the other thing you have to so it is true that mass cannot move through the grid of space at the speed of light, or c, right? It has to go slower than the speed of light, but the grid of space can expand faster than light can travel. There's nothing in relativity that says that the grid can't expand faster than c. Its mass can't move through the grid of space at c. It has to go below, and light must move at c and only c, always c, right? C. So one of the things as well is that the misconception is that the expansion of space does permit objects to recede from each other even faster than light. Now, one of the things in particular to think about is you say, well, how big is the universe? And the honest answer, we don't know.
It's the biggest thing I'm aware of.
Yes, it is. It's pretty big. But what we can talk about is the observable horizon, right? The best estimates based on data and observation is that the Big Bang process has been going on for 13.787 billion years, plus or minus 20 million years. It's 13,787 million years. It's a long time. Plus or minus about 20 million years. That's sort of the error bar.
That's a very that's a 20 million years. That's a very low model of error of reflect. Whatever that word is, I can't.
Yeah, it's a pretty good error estimate. I mean, we started off much earlier with a much higher error bar, right? And part of the golden age of cosmology has been to really nail down that error. But right now we're almost about 1 part in 1,000.
I guess this is a good top. So we're talking about that. I think it's a good time to move on to the next topic.
Yeah, I would just say in passing, getting the error bar that small does require, as far as I understand it, sort of restricting yourself to like the Lambda CDM model, which is the best one, but
yeah,
it's a work in progress still.
and there are other observations. It's sort of called Hubble tension. We can talk about NBE1, where you might say that 20 million year error bar turns about 170 million years. So 13.8 plus or minus 170 million years, right? It's a refinement. And if we find that the number is instead of being 13.787, it's 13.828, that's just fine, right? It's a refinement, not a refutation. The Big Bang model still is there. The universe started off the universe was in, I'm sorry to say start off because it's the bad language. The universe was in a hot, dense state, and it transformed into the universe we visibly see today through a process of the Big Bang process, and that process has been going on for roughly 13.8 billion years. And we'll have refinements of that sort of stuff, and details are being done. That's why we don't have all the answers yet, but we have answered a lot of the questions.
So, sorry, next topic. Who and when did someone say, "Hey, this is my idea. This is what happened back then. Here's my hypothesis." At the time, before it became a theory, of how this all began.
I mean, if you go back through the history of cosmology, the study of the cosmos, one of the earlier interesting theories is called a gentleman by the name of Singer of Brabant had a thesis he called The Eternity of the World around in the 13th century, where he said that there was no first person, there was no first specimen, the universe did not even have a beginning, it's always been eternal and infinite in size, and he was condemned by the Pope, of course, because the Pope.
So this is when people thought the Earth was this is back when people thought the Earth was still the center of everything.
Well, that the universe is always the same. There's a bit of that stuff, but there was sort of like this the steady state thing. The universe is eternal, didn't have a beginning. You also had people such as the gentleman who was burned at the stake in Rome. His name just escaped my mind. And he had a notion that the dots in the sky were actually stars, just like our sun, or objects just like our sun, and that those things had life on there. And he also was a priest. He said they had salvation, blah, 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 blah. And he was burnt at the stake for his heresy as well. Giordano Bruno is his name. You go to Rome, there's actually a statue in his honor, sort of apology, sorry to burden you with this. And you had even people like Newton, who acknowledged that he was very fast in his thinking about the fact that the universe did not start on Earth, right? That the universe was bigger than the Earth. There was a bigger thing, and so moving forward, you have people. You had Einstein, who described space-time in his special and then general relativity theory using equations of state, and basically talking about how mass and how space-time are interwoven and warp and do things that are non-intuitive. And there was a physicist by the name of Lemaitre that people often like to say he was a Catholic priest, I think, because they're trying to apologize for the many crimes that the Catholic Church committed in in his lifetime. But anyway, Lemaitre was one of the people who took Einstein. He was a real physicist. Took Einstein's equations, applied to the universe, and suggested that the universe had to be expanding. Why? Because he said you've got this gravitational force, and if there's nothing else, that everything should be collapsing, right? Gravity should be pulling everything together, together. That's not happening.
Didn't he determine that the universe had to be either collapsing or expanding? And he went with expanding.
Well,
I think, right? Yeah.
And beyond that, he also had Hubble, Edwin Hubble, the telescope's named after, who used observations to note that galaxies were receding in general, that the farther away the galaxy was, the faster it was receding, that the universe was expanding, right? And in fact, it's called the Hubble-Lemaitre law, that velocities have been determined by their redshift, and that Hubble was first of all the first person to having a telescope like the Mount Wilson 100-inch telescope to take pictures of stars in other galaxies. That these nebula things were not just gas clouds, but were other islands, because people at that time thought the Milky Way was our cosmos. These other fuzzy things are not gas clouds in the sky; they're actually their own galaxies, and that he was able to measure the redshift using data that came about by a gentleman named Alexander Friedman. This happened in 1922. So by the Lemaitre came around in 1927, he had the notion of Hubble's thing about the universe expanding, and basically said the universe expanding. Run the movie backwards. The universe had to at some point be in a hot, dense state.
You keep on saying that. What does that mean?
Well, if the grid collapses, right, then at some point, your observable universe, right? What do you mean by observable universe? Since this Big Bang process has been going on for, let's call it 13.8 billion years, it means that we're seeing the limit of our observable universe is photons that have traveled 13.8 billion years. We can't see things beyond that limit because the photons, if they're there, haven't arrived to us. We don't know if the universe is infinite or finite. It could be either, and there's good models to talk about it. But our observable universe has been expanding for 13.8 billion years. It is not 13.8 billion light years in radius. The size of the universe has expanded. The numbers are probably closer to about 68 billion light years in terms of distance, because the grid of space has been expanding for those 13.8 billion years. So Lemaitre was saying, hey, if you run it backwards, the universe was the objects in our observable universe the distance had to be smaller, and at some point had to be very, very small. Now, some people run all the way backwards to zero and say it had to start at singularity. There's problems with singularities. We can talk about it in just a moment. But the model just says the early universe started off a very high temperature, right? Because when you bring stuff together, you're elevating the temperature, and also because things were so close to each other, the temperatures were normalized, right? That is, if some spot was a little bit hotter than the spot next to it, the energy would transfer, and they would normalize its temperature. So everything was in such close proximity space-wise that it was a very that early universe was in a very uniform, hot, dense state. Well, today the universe is lumpy. How do you get from a hot, dense state to a lumpy state? And this is part of the Big Bang model that explains that process. But
the universe today is also very cold, right?
It started off this way. Go ahead.
And the universe is also very cold today. Like it's like almost near absolute zero. Yeah. Most of the universe.
Yeah, we're about a 2.73 Kelvin is the average temperature today. Now, when you run the thing backwards, temperatures rise. For example, when you reach a point where you're running the movie backwards, the universe is at, let's say, something around 5,000 to 6,000 degrees Kelvin, I think is the temperature, you find that even like hydrogen atoms can no longer stay atomized. That the electron, the hydrogen atom, a proton electron pair, that is so energetic that electron takes off, right? And atom
becomes
no
a
longer,
plasma.
you get what's called a plasma.
Yes.
And in fact, one of the things that the Big Bang model implied was, if you run it backwards, at some point, the universe is such a hot, dense state, there's no atoms, you just have nuclei, you have charged particles, things flying around. Photons can't go anywhere because they get interrupted and reprocessed and so forth. So the result is you just get a plasma soup. If you've ever seen a really hot kiln or a blast furnace, look inside, what you find is that you have no detail, or you just see glow. You just see a fog of stuff at super, super high temperatures. And that's what the universe was. But at some point...
It was opaque. It was opaque. You couldn't see through it. It was like
Yeah. And at some point, the universe cooled. Why? Because it's expanding and cooling. Same amount of stuff now in more space. And that it cooled to the point where those lone little protons could grab a hold of electron with enough oomph to hold together and form neutral hydrogen, right? This is this point, and we'll talk about this in BE2, but this is the point where the first atoms formed, and the photons that were trapped in this plasma went bing, and we get the Big Bang flash, right? It's one of the predictions of the Big Bang model, which was been confirmed. But the universe...
It is called recombination, right? Like the moment when basically all the electrons were confined into the neutrally charged atoms of hydrogen and helium.
And we'll talk about this in BE2. But yes. Go ahead.
When was that idea? I think it was sort of hinted at in I was doing some research on this the other week or month or something, and it was my understanding that it was hinted at sort of kind of by a physicist in maybe like 42 or 47 or something, but that it wasn't really proposed as like we expect this afterglow. That it wasn't sort of explicitly predicted until right around the same time that it was just discovered, though. Is my timeline on that correct?
You have people talking about the implications of the Big Bang model in the 40s, 50s, even the point of 1960, where they were talking about this, and the competing other model was steady state. And it was the other main model at the time. And so there's discussion back and forth about this thing. Again, not a debate, not a vote, because that's not how science does. But people saying, well, if the steady state model is correct, then we should see this. If the Big Bang model is correct, we should see this. And people talk about what's the implications of this model. And one of them came about was the microwave background radiation, the CMB, that was predicted that the steady state model said shouldn't be there, right? Because again, why? Because the steady state model was the universe is always there, it's infinite, and when they say, hey, the universe is expanding, they say, well, okay, there's matter being spontaneously created so that the universe stays nice and normal. Which is obviously now not considered to be scientific, or not scientifically valid. Whereas the Big Bang model said, running the film backwards, there got to be a point where it was this case. But there's other things as well that we get into atomic physics in BE1 and BE2.
So how long was it between when they first proposed the idea to when they discovered the idea?
It depends a little.
The first, other people has sort of the big notions of stuff, but the first real scientific physics, papers, equations, blah, 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 and justification for this model was George Military in 1927. The implications were people said, well, that's nice, but that sounds absurd because da 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 da, right? And back and forth testing of the model, refinement of the model, and it wasn't really until probably the discovery of the microwave background, cosmic microwave background. That was kind of the first time people said, oh, and so 1965 is when Pindus and Wilson, they started working in the 1940s, by the way, because they were trying to say, hey, they're part of the telephone company. And they thought, rather than swinging copper wires around the country, if we could just use like light in the form like microwaves, we could send stuff point to point without wires, and wireless telephony. And so they built things that operate in what's called the microwave part of the spectrum. It's higher frequencies than radio, because radio is noisy and has all kinds of stuff. It's lower frequencies than infrared or light. But they said, let's look at the microwave and see if this is useful for building a telephone system. And they kept finding this hiss, this noise there. And so they tried to say, well, and so that was Bell Labs. They said, well, let's find out where this noise is. What is this noise? And maybe it's a frequency we can ignore or move around or so forth. And so they started looking for this noise. And but again, it turns out that was one of the things that was discovered 1965 that the Big Bang model had predicted, and the predictions were being discussed in the 1950s to up into around 1960, where they sort of said, yeah, if the Big Bang model is true, then this should happen, right? And
they were sort of in like a sort of like an afterthought kind of way.
Yeah. They weren't probably they were and we'll talk about it again in BE too. But those Bell Lab scientists were about trying to find out what the noise, how to limit this noise, so we can use a telephone system with microwave links, and so they were looking for the source of it. And
now, I think you mentioned during our pre-show discussion that it's very similar to the snow on old school TVs.
Yeah. In fact, if you have a television that has an aerial, right, antenna, right, as opposed to cable or internet stuff, and you tuned it between channels, so you had basically static, you'll see that snow on a TV, and about 15% of that snow is generated by the Big Bang process. But back to say, so that was the time experience for it. I think again, it's important to deal with the misconceptions, right? That of stuff. The thing is that the Big Bang did not occur at one point. The Big Bang encompasses the universe of all space-time as we know it, and that it's beyond the realm of the Big Bang model to describe what gave rise to the Big Bang process. That's outside the model. Now, there's speculations about that, right? And one of the ones that I like, probably the best, because I think it has the best evidence, is the Hartle-Hawking proposal. So someone says, well, what happened before the Big Bang process started? And the Hartle-Hawking proposal, the universe has no origin as we would understand it. So that saying that the expression, what happened before the Big Bang, has no meaning. So what do you mean it has no meaning? You just said it's been going on for 13.8 billion years. What happened with 13.8 billion years in a day, or whatever the number is, right? Beyond that. And the best way to describe it is that the conditions of space-time certainly curved in to a dense state, but to ask what happened before the Big Bang process started may be irrelevant. Sort of like saying, when I was walking towards the South Pole, I've been there multiple times, multiple visitor. Sorry, flat earthers. It really does exist. I've been there many times.
Yes.
When you walk towards the South Pole and identify where it is, I live in about a centimeter or so. Walk towards it, and you ask, what's south of the South Pole? Now, I've walked through the South Pole, gone out the other side, back and forth, right? That's but to ask what's south of the South Pole there isn't. It's by definition, the South Pole is the most south part on the Earth, right? So if the Big Bang process creates space-time, so space and time are established as part of the Big Bang process, the time before the Big Bang process started is irrelevant. It doesn't exist. It's like what's north of the North Pole, what's south of the South Pole. Well, nothing. I know that people would like to think that, and this is back to steady state stuff, that time is eternal. But that's an assumption. Now, there are other ways to cut it. There are models beyond the Big Bang, like cosmic cyclic cosmology and things going back and forth and so forth. But the history of the Big Bang process just talked about that you run the movie backwards, you end up with a universe that's hot, uniform, and dense. And the physics of that is very weird. Some of it is non-intuitive, but all the atomic physics and all that high energy nuclear physics stuff gives us insights into some of that early universe.
Yeah, as we went on, we found out it was much smaller and much younger. First of all, I think sometimes the older ones were like, it was like 20 billion years ago or something like that, and they got less, more recent thing, and then
because part of the thing is early on the rate of expansion had a lot of error, right? You've got a dot and a dot, two dots, and you draw a line, and the lines had error bars, so you had lines that could intersect back to the origin in different spots. We had situations where the slope of the line looked like it might be the Big Bang process was going on for maybe as short as 10 billion years, right? Some of the lines were on the order of 40 billion years. But at 10 billion years, we had problems because we have stars and clusters that were older than 10 billion years at the time. So we knew something, that line was absurd, right? You can't have things in the universe older than the universe. But the refinement has occurred in terms of not only the length of time the Big Bang process has been going on, but also that is not a linear line. So you're running the movie backwards. The frame rate, if you will, of the Big Bang process has changed, and that's probably one of the big things that happened, because in about the 60s, in the 1970s, early 1980s, the debate was, okay, the universe is expanding, but you have gravity. Is the universe decelerating, or gravity is going to grab a hold of stuff and start to pull it back? Even if space is expanding, grab a hold of matter and force matter back into a big crunch, right? The universe was, if you will, closed. The matter would be drawn back into some spot. Or was the universe expanding and open and just keep going forward? Remember, by and large, stuff in space stays where it is unless something's pushing on it. And the grid is expanding, but the question is, could gravity grab a hold of stuff and begin to draw it through space into a crunch, right? And this open-closed universe, which was debated, it wasn't until the discovery of the accelerating universe and what we call dark energy that we realized that both of those concepts were wrong. And to my astonishment, that not only the grid of space expanding, but it's getting faster, right? About 5 billion years ago, it appears, gravity lost its slowing down grip, and the universe is now beginning to accelerate and getting faster and faster and faster. And that's
I have heard that the galaxies within our local group, like the Milky Way and the Andromeda galaxy, and also a few other smaller galaxies in the local group, they are gravitationally interacting with each other, such that they will eventually collide. But all the other galaxies, they will just move away from us.
Yeah, because
Forever.
the grid of space between galaxies in its own cluster, or even between clusters of galaxies, is relatively bound together, right? And the things are going to be, gravity is going to hold them together, right? It's that typically where you see more of the expansion is between clusters of galaxies, or between clusters of galaxies in a larger scale. We'll talk about some of that in BE3, but that's really the essence of it, is that Earth-Sun distance has been pretty much consistent over most of the life of our solar system. That's not getting bigger, right? You getting bigger is not because of expansion of space. It's probably because of you eating more than you're exercising. That's how you get.
It's also the case that the gravity gets very weak with greater distance, but the expansion of the universe, like it scales with distance. The further you are away, the faster you're moving away, so to speak.
Yeah, and so in our local cluster of galaxies, they're orbiting each other and moving around like a little beehive thing. That gravity has enough binding energy that those things are going to stay pretty much in that state, spinning around. And it's going to be the distance to the other clusters of galaxies that's going to be expanding. And that's within a supercluster, and the distance to the other superclusters are expanding. That's where the grid of space is more effective.
It's also very sad implication, because like if you think about this, like after many billions of years later, all the other galaxies will have moved away so far that we won't be able to see even their light anymore. So the whole universe will only be our own galaxy, and no other galaxy will be visible.
Of course, by then, I don't think we as humans probably won't be humans anymore.
But moving on, that objects will become more and more redshifted. It'll be fading away in a far future. But there's many other problems that occur between now and that spot, as we pointing out.
Yes.
So before we move on, do either of you have questions about history, the theory history of this event, how it came to be, as scientists know it? Any questions?
Yeah, we're gone from Einstein.
Not regarding the history, but I have a few other questions. But if
the summary is Einstein's equation, probably the good place to start. Hubble detecting galaxies, expanding, Hubble Lemaitre redshift, Lemaitre proposing the model, debate between that model and steady state, observations that favor the Big Bang model and not the steady state, and then further refinements to even acceleration and discovery of dark energy, and on and down the line. It's kind of the history of stuff.
I remember this, like you mentioned Einstein's equations, and I believe, if I remember correctly, that Einstein himself didn't believe in like a changing universe. He also believed that the universe was static, so he had to come up with the cosmological constant to maintain the static universe, basically, right?
Einstein's favored the time that he was pretty good for his general theory of relativity. Agreed with or thought that the steady state model is a reasonable model. And his equations, however, suggested that the universe should be collapsing. Gravity should be pulling
intrinsically. Intrinsically, the only stable solutions are either an expand. Before he added the lambda cosmological constant, the equations are very clear. They tell you it is either expanding or it's contracting. Maybe it can switch between the two, but if it's going to just stick around and chill, then you need to add another thing.
There is no stable state that can remain the same. Basically, there's no stable.
You're balancing both sides of the equation.
Yes.
So Einstein at the time, and then that was a predominant assumption at the time.
He asked around.
We look at the universe; it seemed to be pretty steady state, and so the equation must have what you call a fudge factor, right? Now, when Hubble demonstrated the universe was expanding, they said, oh, okay, I don't need the cosmological constant. That's my greatest blunder. Throw it out because the universe is expanding, and that's why the universe is not collapsing. What he didn't realize was that, in fact, it was wrong, and his greatest blunder was, in fact, removing the cosmological constant. We now know the cosmological constant is a fundamental part of the equations of state of the universe. And in fact, it's a dominant state. In fact, most of the universe is the model, right?
But like that cosmological constant is representing the dark energy, quote unquote, right? Or
Yes,
am I mistaken?
Yes, but it's mathematically the same entity.
Yes.
Yeah. Now there's different interpretation of that, and you're measuring when you begin to measure the expansion of the universe more carefully. You start to get to some error bars we're trying to resolve. So it's not, and the press does this all the time, where they sit there and say, "Oh, new observation throws out, invalidates, blah blah blah." Like, no, there are observations with these data points coming in, just like early Big Bang model stuff. When you did the slope of the linear line, you got a 10 billion year old universe, and say, yeah, but this cluster is 12 billion years old. Something's wrong. We knew there were errors there. We know there's errors, and there's tension in there that we're trying to resolve. But this is the scientific process, right? This is what science does. It's not throwing out stuff. It's not invalidating the Big Bang model. It's refining it.
Mm-hmm. Oh, I have a question about the expanse of the universe. Is every single place in the universe expanding at the same rate, or different places are expanding at different rates? Maybe
that's a really good question. So there's a team led by Adam Rees and Alex Filipinko, a wonderful professor at UC Berkeley. And if you ever have a chance to take one of his courses or go to one of his lectures, you go to his lecture even you understand the topic, because the way Alex Filipinko explains it is just wonderful. He's a fantastic communicator. Okay. But anyway, back to the plug.
All right.
They're looking at the refinement to ask questions like, is this dark energy, the supposedly process by which the universe is expanding and accelerating, is this dark energy is it consistent in all directions? If we measure dark energy in different directions, do we see the same amount of expansion? Is it consistent over time? And so is it constant? The answer so far is it's reasonably consistent to the error we can measure it, but we're trying to get more refined and understand it as to whether or not dark energy is there. The other thing about dark energy is asking questions in the future will be as strong. I must say that the dark energy was a big surprise to me. In fact, to find it almost about 70% of the universe was something we had completely missed, right?
Dark energy is one of those examples where it actually would have been reasonable for the journalist to publish this. Maybe doesn't change everything, but it was a big surprise.
Yes.
It fits into the framework, but it was not. But you have to modify the framework somewhat.
Yeah, because in the 70s, even in the late 70s, I thought the data coming in favored an open universe. Well, we didn't realize that was wrong, and that the universe actually is accelerating, right? It's not even neither closed or open, it's actually ripping. Now, will it do that forever going forward? Well, it's hard to say, because if we don't understand the process now of dark energy, it's hard for you to make statements about what's going to happen in the future, let alone in the past. But the current observation said that around 5 billion years ago, gravity lost its contraction fight with the expansion of the universe, right? That is it dragging it down, and that this dark energy is taking over. Now it is as if, but again, this is an analogy, not a statement. It is as if space itself is repulsive to itself. that space repels itself, and that you could argue this is an interpretation that as our observable universe is expanding, there's more space, and space is repulsive to itself, so it gets even more stuff, right? It is now the question is, does that mean it's going to go at some point, accelerating up to stuff and have a big rip? There's arguments saying no, but this is now way in the weeds of theory.
I believe the idea of the big rip is that eventually the universe is expanding so fast that not even the force that binds the atoms will be able to hold, right?
Yeah. And so there's been some good arguments and papers published saying that may not be the case. Now, I understand that the assumption that dark energy is going to operate the way it is now in the future,
assuming we understand it now,
is another assumption, right? Because some people talk about, and we'll talk about in BE1, the era of inflation. Some people argue that era of inflation was an example of a dark energy that switched off and then switched on. And the question is, will it do that? Is it an open question? But see, these are not things that you validate the Big Bang model. These are refinements in people doing research. So that question you asked about is the acceleration of the universe, or even the expansion of the universe, consistent over space and time? Answer is we don't know, but we're measuring it. And so far, it appears that dark energy is consistent in whatever direction you look, and that dark energy is getting stronger.
All right. Well, we can come back to this at the Q&A section, but I think we should move on to the next part. The next topic we had was no, that was wrong. Nope, that was right. Never mind, that was right.
So what preceded the Big Bang, if anything? That question may not be valid. It's a question, but it may be under a false assumption, right? I think I see the great credit in the proposal done by Hawking and by Arta, that the universe really did not. There really was not a beginning of that the Big Bang process established time in the first place. That is, in the early moments of the Big Bang process, space and time were established. Now, you can say what happened a trillion years ago, but that's like saying if you walk 1 billion kilometers on the surface of the Earth, do you get to the edge? No, right? You can have things that appear to be infinite because you can go around the Earth as long as you want. You're not going to get to the edge. Sorry, flat earthers. But the notion that, did this Big Bang process, if the Big Bang process established space and time, right? And one interpretation is that the Big Bang process established even infinite space and time. Then asking what happened before the Big Bang is like asking what's south of the South Pole or what's north of the North Pole on the surface of the Earth. I know it's not a very satisfactory thing. Now, there's other things that talk about many worlds and cyclic cosmology and the multiverse and other things like that. The Big Bang model and theories around the Big Bang don't address before. Some even say there isn't any before, right? The Big Bang process even created or established, a better word, established space and time as part of the inflaton field stuff.
I've also heard about I mentioned this in the off air before we went live about two different definitions for what the Big Bang is. Like you have the the common conception of Big Bang, which says t equals 0, the first instance of the universe, basically. But you also have the second definition where it refers to when the universe was hot and dense. Basically, the hot Big Bang version of the definition. And that, according to that definition, you may have something called inflation before that hot, dense state of the universe.
And there's also a model that says that the Big Bang process didn't happen once, but in a multiverse, it's happening all the time. A little, if you will, Versailles popping up with their own little Big Bangs, and we have.
And that reminds me of I've watched BBS Space Time YouTube channel, and you remind me of a thing that they said about if inflation is real, perhaps inflation is happening infinitely, and you have different batches where the hot Big Bang is established, basically everywhere, like bubbles in a boiling pot, basically.
And understand, these are really valid questions that cosmologists are wrestling with. The Big Bang model and Big Bang doesn't address it. It's outside the model, but it's interesting to ask. And you raise good points. And people are asking about this and trying to know. There's a thing there's an assumption that the universe is explainable, right? Some people assume that the universe has an explanation. There's a closed form formula someplace. There's a thing that says, here's the universe, done, right? And I think Douglas Adams' humor sort of says that if you ever did that, the universe would change itself, right? but yes, the assumption that the universe has a infinitely precise, complete definition is an assumption, right? We may never be able to know why the Big Bang process started, right? We may be able to establish that the Big Bang process started time itself, and therefore asking what happened before the Big Bang is irrelevant. Or it may be that the universe is part of a multiverse and stuff. You don't know. Now, there's another bit as well. People, if they run the movie back far enough, it would imply that the universe was at some point zero, had the universe, and let's be careful, right? The universe could be infinite. What is changing is the horizon of our visual horizon. The universe could be infinite, right? And that the Big Bang process could create an infinite universe. So there's nothing for the universe to expand into. It is infinite, is one model.
And it always was.
Yeah, and always is, right? What's there is that the Big Bang model established stuff which ended up becoming atoms and stars and all kinds of cool things like that. Literally cool, right? But it started off in a hard dense state. Now the question is, if you use the mathematical line and assume that math is how the universe works, you would run it back to the point where they call it T equals 0, where the temperature is infinite, the density is infinite, and you got this singularity. And I am reluctant to state that these singularities, these points, are anything other than mathematical artifacts. Feynman kept
the North and South Pole are also singularities because you have the lines converge to an infinitely small point, basically. Yeah.
And Feynman reminding me the universe is under no obligation to follow your hypothesis, right? You can come with all this math, but the universe doesn't have to pay attention to your math, right? It's your job to try to model what the universe is actually doing. The universe doesn't have to pay attention to what it is you're doing. So the notion of, well, the math says blah, blah, blah goes into an infinite point, singularity. That may not be correct. I suspect from a quantum mechanics point of view, once you get shorter than Planck length, Planck times, Planck distances, that things get really weird, and that the universe does not allow you to have infinite points.
So
These things. I also, and I think, by the way, there's been some really good arguments made that some of the models put forward about singularities are wrong.
Kerr has made a big stir in the last few weeks.
Yeah,
talking about
straightforward arguments.
Yep.
I am not impressed by Roger Penrose's musings on cosmology in the last decade or two, not because he's a smart person. He's a very smart person, very active stuff, but because he proposes things he knows are wrong. Why? Because we have evidence that shows it's not correct. Sorry, right? There's a bunch of stuff, and so his quote theorem about that singularities are in the middle of black holes, basically turn mass into a singular spot, an infinite density of things, appears to have a very significant flaw, and that is not a proof. Of course, science doesn't really prove things. There is good arguments to suggest that's not the case, and that something else happens before you get to that mathematical point. Again, the universe does not have to obey your equations to do what it does. The universe does not ask you permission to do what it does. Your job is to try to model what it does, and don't assume that your math is what the universe must follow.
Any questions before we move on?
I had some questions about the current topic is well preceded the Big Bang, and I've heard about speculated epochs before before the hot dense state. You had the Planck epoch and the grand unification epoch, speculated epochs.
And stay tuned for BE1 show, which is in a month from now, because that's when we're talking about the fraction of a second in the early part of the Big Bang process. We're going to be talking about those sort of things, those epochs, right? But there are predictions, and we have alterations and accelerators and atomic physics and all kinds of nuclear high energy physics gives us insights into that stuff. It's one of the fundamental reasons why you want to build accelerators and do things, because you are creating conditions that are similar to the early universe, right? And so we'll talk about that in definitely about in BE1. It's a great topic.
All right. So the next topic we had on our to-do list was
what might have been the cause of the Big Bang?
I know what some people say, but
the Big Bang model and models and the physical theory of the Big Bang does not address this question. This is outside its purview, but it's important to ask.
Do we have ideas again? The main idea behind the Big Bang is basically that the universe is expanding.
The universe started.
So we can ask why the universe is expanding.
So we have ideas beyond. So we do have ideas beyond saying God did it.
Again, the Big Bang model says the universe was in a hot, dense state and has evolved from that point, and that the universe we have today is a consequence of this Big Bang process, and the Big Bang is going on right now. Right? It's not that it happened back then. It's a process happening now. And you say, well, what might have caused it to come about? And some people say, well, so we're talking about models that are not part of the Big Bang. Kind of slightly off topic, but let's entertain the question anyway. One of them says that there was a quantum fluctuation, right? And that the Big Bang process started by a quantum blip. The quantum mechanics typically does not allow you to say with infinite precision, infinite precise stuff, here is an energy state at this point, at this place, at this time, right? You're not, that's to say, I observe this particle, it is exactly here, and it's going this direction, at this speed, with this momentum. Quantum mechanics says you do not have an ability to make that precise statement. In fact, it is not that you're not clever enough. You didn't try hard enough. It's not that you didn't do it carefully enough. The universe does not have an answer.
Yeah, it's fundamental to the structure of how reality, physics works. And exactly what it means that you can't measure position and momentum both arbitrarily accurately, and the fact that you can put a number on it and say that the product of those uncertainties has to be larger than like h bar over 2 or something is remarkable, and it is something that is very natural from the math and leads to a huge host of questions about what it means. And the concept of complementarity, I have a book here actually from Max Jammer about the philosophical interpretations of quantum mechanics, and there's like chapter 4, the entirety of it or something is like about the principle of complementarity.
Sure,
it's fascinating.
And quantum mechanics is very unintuitive. Probably the best, and unfortunately, part of the best ways to try to understand quantum mechanics is to look at the math.
Yes,
because the universe is not intuitive. What you think should be the case of, you have a baseball flying by, and you say, well, of course, I can do a really careful snapshot and position and tell you exactly where that baseball is and how fast it's going and where it's going to go, right? And the upshot of quantum mechanics is there is not an answer to that question, right?
Yes.
There is a particle. What is this momentum?
They are not defined.
The universe doesn't. You're not going to get an answer, right? There's not answers to every question. I know some people philosophically and spiritually want answers to things, but the universe is under no obligation to give you an answer to every question you come up with. Sorry.
I think it's like asking like what direction is up or down in the universe. Like there is no up or down in the universe, basically.
And a lot of things, in general relativity and special relativity, when I teach you that stuff, one of the hard things to get across is that everyone's frame of reference is equally valid.
Oh,
there's no master clock. There is no master grid of space. There's no origin. There's no. And we have baked into our brains so deep, it's hard to get rid of that stuff. And you keep finding when the students going back to saying, your clock and my clock are both valid, right? The notion that time is absolute and space is absolute and there's a master grid and origins over, no, wrong, right? Even though mathematically you might probably want to describe a grid with an origin. Everyone has their own origin. Everyone has their own time. Everyone has their own clock. And it's real. It's not just this fake Star Trek stuff, right? It is real. It's experimental. It is for example, why current in a wire generates a magnetic field around it because it's relativistic effects. It's beautifully measurable. Same thing with quantum mechanics. The notion that something is there, like an electron is there, is wrong because its electrons can be described as a point-sized particle. It is described as a wave, and both are valid. In fact, it seems to do both at the same time. The universe is surprising. Now, why is this relevant? Because some people have speculated the reason why the Big Bang process got started was a quantum mechanical blip. Because quantum mechanics doesn't allow you to say there is zero stuff here, right? There's nothing, right? Even empty space is full of stuff.
The vacuum state is very interesting.
Yes, it's very unintuitive. There is no the notion of nothing, right? In physics, quantum mechanics says, well, wait a minute. What do you mean by nothing? Nothing would be zero energy. You can't have energy. You can't have absolute precise energy level. No. Right? And in fact, you can measure that there's these particles that kind of they like embezzle the energy, create a pair, and stick it back before someone does the accounting and find that someone had pulled money out of the till and stick it back in. Right? It is bizarre. And so people say, well, that vertical particle popping out, which we can actually measure, it's not just some wild ass concept. It's actually measurable, demonstrable, and observable. That may have been the cause of a Big Bang.
I've also seen a different answer. Like again, a video that I've seen on PBS Spacetime. It goes back to the inflation is still a bit iffy, of course. But if you assume inflation, and we assume that inflation was driven by an inflaton field. I'm talking from memory.
Yes,
and basically what happened was this inflaton field has an energy which caused exponential expansion in the inflation, basically. But at some point, you had a quantum fluctuation that caused this inflaton field to collapse, and that collapse stopped inflation. But this collapse of the inflaton field also generated all the elementary particles and that established the hot, dense state of the universe.
And we're going to visit that topic in BE1 and spades there. So we're not, you're not done with the Big Bang process. The Big Bang process is going to be going on through this entire show, but that's an important point that has to be considered, and that's been, we have interesting measurements on that. There's another thing that's talked about, that the universe is multi-dimensional, and you have these things called brains that collide. When they collide, they create little Big Bang universes as part of a multiverse. There's a many worlds interpretation of quantum mechanics that talks about the universe forking and doing stuff. There's a lot of models. Understand the Big Bang model and the Big Bang theories that come from that model do not address the cause. They address the effect. The Big Bang model says, again, the universe was in a hot, dense state and has evolved to the current state through this process. That's what the Big Bang model is. It doesn't say how it got there. It doesn't say what happened before. It may not even be valid to ask us before. We don't know. But it's being actively investigated. It's not being
for now, Ty, let's go
to
the next topic we had on the thing, which was
cyclic cosmology. So this is something that Penrose particularly has been championing. And it's the notion that the expansion of the universe stops and reverses itself and goes back in, or that the expansion of the universe rips and you get a new Big Bang coming out of it. That the universe cycles through what he calls epochs, where we're in one of the epochs, right? And that there's one way that the universe might go into a big rip, far down into oblivion, and popping out of that thing will be another little Big Bang process in another universe.
So what is an epoch?
Would be a cycle. According to Penrose, it's this cycle of the cyclic universe, right? That is, the universe goes from the basic, because if you just keep the universe expanding, the temperature lowers and lowers, becomes more and more uniform to the point where there's not enough stuff to do anything anymore. You basically get a dull gray.
Now it would appear to be static because nothing happens.
Yes.
Nothing appears to happen anymore.
and somewhere in that thing, then one way. So that's one model. It says somewhere in that process, you get another thing that happens and another Big Bang process. The other way is to say that the dark energy reverses itself and goes from from expansion to contraction and comes back in a big crunch and goes through another Big Bang. That's another mini worlds.
Like I think like the first idea is basically saying like, according to quantum observations, that there's a very extremely small likelihood that a new Big Bang will happen in the universe. But of course, but when you are speaking about like infinite amount of times and in an infinite space, basically, it's guaranteed to happen eventually in a very distant future.
Or that the notion of dark energy, or that the expansion of the universe, accelerated universe, is going to always go on, is an assumption, right? And someone point out saying, hey, in B1, you're going to talk about the inflation epoch, and that stopped and it kind of came back again. Who's to say that this thing that always goes forward, right? It may be that dark energy is going to call a halt to the expansion of what? The expansion of our visible universe, right? Again, the universe may not be expanding into anything, right? It could be infinite, right? It's our horizon, visible horizon. See that given the amount of time that's been going on, that's our expansion. And it could be that thing stops expanding and comes back to a big crunch and goes through another Big Bang process again. That's another way of talking about cyclic cosmology.
What do you personally think? Like, do you think the universe will just stay in the heat death forever, or what do you think personally?
I think the data most favors the heat death, where the universe just continues to expand. Stars eventually go out. Things wander into black holes. Black holes evaporate, and you've got basically a
infinite
sea of photons whose energy isn't big enough to do anything other than say, yeah, there it is. You go into
like would the photons go for like eventually they will lose, like they get redshifted to infinity.
Yeah, and they get to be so weak in doing things that because at least you get really energetic
will the photons disappear? Will the photons disappear basically, or
no? They just get weaker and weaker. Their wavelength gets lower and lower, right? That the stuff gets spread out. The energy density gets spread out to a point. Because in high energy gammas, you can get high energy gammas, and we observe this and other things where you can get them to interact and create an electron-positron pair, right? Equals mc squared. You can take energy and get matter out of it. But at some point, if the photons are so weak to not even do anything, right? The matter has, because one goes speculative, even the proton has a lifespan and decays, right? And that the particles become, and the question is that matter wanders into black holes. Black holes evaporate. And one thing that Hawking probably did best, his work, was to say that black holes are not black. They have a temperature and they slowly leak. And so the universe has kind of doomed the model that seems to be best corresponds to our current observation. There may be new observations that change it, but the current observation says that the stars are going to eventually stop popping out in existence. Things will be too diffuse to even create stars. Material is going to wander in, be sucked into black hole event horizons. Those black holes then decay over time. And we're talking about like 10 to the 100th power, 1 with 100 zeros years type of time in the future, where the black holes have just evaporated. And what do you have? A bunch of weak photons that are too weak to do anything interesting. And the universe gets to be basically a dull gray stuff.
All right, so before we move on, any questions about this topic here?
But we don't know. Active research, Big Bang model doesn't address this thing. These are people asking about the implications of the Big Bang model and critically going back and forth.
All right, so now for the next topic. For the next topic, I'm guessing here that this is different from what the comic book universe says that multiverse is.
Yeah. Multiverse, right? Is our observable universe the only thing? Is it possible that there is a larger scale structure where Big Bang processes are starting. And these things are too far apart for their event horizons to interact. And so these are islands, separate islands that don't interact. If there's another universe out there, there's no evidence that we've ever interacted with it, right? If you never interacted with it, it might as well not exist from our standpoint. I know I make a joke of saying this is my favorite universe. It is, and given I have a count of 1, this is my favorite. But I'm not saying that there isn't more. It's just I've never experienced them, and who knows? Maybe it'd be better if I knew about another universe. That might be my favorite. But currently, this is my current favorite.
I guess think, like one. Oh, so go ahead. Sorry.
I was going to say that I think that there can sometimes. I think that the word multiverse can mean different sort of things in different contexts, and so in a cosmological sense, also, it can mean something that is different, or it's sort of a spectrum. It doesn't necessarily mean the same thing as people mean when they talk about like the quantum multiverse, which is a position that I sort of hold to, but I would not describe it as what people sort of imagine as like a different, like a parallel universe where like you could go to or something. Although, I mean, it's sort of parallel in some sense, but they're all here right now, but they exist in like a way that doesn't, that by definition sort of wouldn't be detectable in the quantum multiverse.
Yeah.
What I mean. So like if you flip if you do if you're doing the experiment where you send a single electron through 2 slits and you watch them interfere with each other, and then you measure, okay, it went through that slit, then people are like, okay, well, the wave function collapsed or something. When really I think what's happening is there is an entirely different branch of a much larger wave function than the one you're doing math with in your laboratory. And
there's a many worlds interpretation.
Yes, they're all sort of happening simultaneously. A cosmological multiverse, you could also explain, I think, from that idea, but it isn't necessarily the same thing. And I think like the idea that you could have different ways that the universe has been realized, is along those lines.
And I know that people have looked for saying, well, maybe there's a Big Bang that happened nearby, and that the 2 things have collided, and we can see, but we've never observed, even though Penrose would like to think we did, we've never observed statistically that our so-called Big Bang is interacting with another Big Bang, right? We don't know. It's a speculation. Again, the Big Bang model and theories don't account for what else besides the Big Bang is there. It's beyond the model.
So how is the real multiverse different than what the movies and comics call the multiverse?
Oh, I think science fiction is a great art. It really has great imagination. It comes up with really interesting concepts. And sometimes people look at science fiction and ask, can I do science to validate or refute that, right? So there's value in this speculation. It may be that this is beyond the realm of physics to decide. I don't know. I'm not going to say no. I'm going to say I don't understand the physics that would allow a multi-universe to exist. And I don't understand quantum mechanics enough. I know enough about quantum mechanics to know I don't understand quantum mechanics to detail that allow me to.
Wait, are you saying you don't know everything?
Well, in fact, that's the Feynman's kid was big of saying is that the more powerful thing you can do is to say I don't know, because if you know,
I've 2 questions.
Not science.
My first question is that, like, of course, the many worlds interpretation would suggest that the other universes are very similar to ours, but in different ideas, would they say that the other universes are very different in terms of the fundamental physics? Like, do they perhaps have different constants, perhaps, or is it just pure speculation at this point?
Well, certainly, one of the fundamental things about cosmology is that the universe is consistent over space and time. The the way the universe works is consistent. It just doesn't decide, oh, I'll do this tomorrow, right? There's a consistent process. And if that's the case, another assumption is that constants are constant. What do you mean by constants? Well,
the speed of light would also be the same in other universes, or could it be different?
I talk about this universe. The speed of light is consistent.
We check that. That's something that we check, and we have error bars on it, but it's something that we keep in the back of our mind, because if somebody finds good, compelling evidence for a time-dependent speed of light,
that would be really exciting.
It would be very exciting. It's the possibility that some of the crisis in cosmology might have at least some of its roots in maybe a time-varying gravitational constant is one that I've heard kicking around just very recently.
The other thing is that the era of recombination, the Big Bang flash, that the physics around that may be not as precise as we think, and that there's errors in that time frame, which may account for the.
I guess that's also the case that the universe is almost homogeneous, but not perfectly, such that there at different points in the universe may have cooled earlier than others.
Yes.
Like a recombination would have happened slightly earlier in some places and slightly later in other places, right?
Yes, and we will see that in BE1. We'll see actually pictures of that, and that's going to be really important, because by the time we get to BE3, the structure of the universe, those little things are going to be big things, right?
But I also the second question, and it's more like I've also seen videos by Sabine Hassenfelder. I think you also are familiar with her. And she lambasts the idea of multiverse as a religious idea.
Well, I mean, she's to be fair, she's her channel, which I highly recommend you subscribe to. She is questioning whether or not that's science and not science fiction or speculation. But I think there's something to be said for that.
You can disprove the multiverse.
I'm not a proponent that the multiverse actually exists. I'm waiting for something to be able to be testable, right? Things that are not testable, I find to be less interesting scientifically, right? If I can't make predictions and test those predictions, it's hard for me to get excited about that.
Yeah, it's. I think it's fair to say that the idea of a multiverse is at this point beyond scientific inquiry, I would say.
Yeah, I'm not to say it's impossible, right?
Yeah.
I don't understand the physics that would allow it. Just like people say, can you go faster than C? And my response is, I don't understand the physics that would allow the fundamentals of special relativity to be violated. I'm not saying it's impossible. I just don't understand the physics for that. I'm not going to be so arrogant to say no, right? I'm not going to be so arrogant to say there's only one universe. Just like people who said there's only one universe, it's the Milky Way. Stop asking questions. No. It's important to ask those questions, but understand the difference between science and speculation. Great for science fiction.
It also depends on what you mean. The many worlds interpretation of quantum mechanics. If you demonstrated that a non-unitary evolution of a quantum state, for sure, that would violate the Schrödinger equation, and very rapidly, I think most physicists, once they became convinced that yes, you can have non-unitary evolution of a quantum state, that they would be like, okay, well then no, then I no longer have any reason to believe in the multiverse. It's actually just a consequence of the fact that those branches of the wave function evolve according to the Schrödinger equation, and we have no evidence against things evolving according to the Schrödinger equation yet.
Yes.
So,
it's like quantum mechanics is difficult in part because it's non-intuitive.
Yeah.
Because the words that are used for analogies are really highly cringeable, right? Cringe
Yeah.
means
Yeah. So if I understand correctly, like the Copenhagen interpretation says that the wave function collapses, but the many world interpretation says that each option is equally real, basically.
Yeah.
Each.
Yeah, nobody holds to the Copenhagen interpretation. Like, actually, it's just the nice way of saying shut up and calculate, so that the students will understand how bras and kets work together.
Yeah, it's the expanding balloon analogy of something. But it is, quantum mechanics. One of the difficulties is it's non-intuitive, and that you really need to pay attention to the math, and the math takes some effort to go forward.
I think it's more intuitive than special relativity, personally.
Yeah, because I was fortunate as a kid to run into Feynman, who I was actually at Berkeley, and he sort of said, I learn by teaching. You have not yet had full physics of stuff. So I want to teach you relativity first, so that you learn relativity before you go into education system where they give you Newtonian mechanics and you get your mind messed up, right? And so and basically he was forced to come back, and he would give me these little talks, and he would give me problems. And some of the problems, he said, are trivial and expect you to come with an answer. Some are difficult, I expect you to work on them. Some of them are unsolved, and expect you to explain to me why they're hard. I'm not going to tell you what is what, right? And so I had this crash course in special relativity, and the way that Feynman presented it was obvious, right? To me, it was special relativity. When I teach it, folks, it's fairly straightforward once you get rid of Newtonian ideas about absolute stuff, right? And I can remember Feynman yelling, saying, "There is no clock. That's out of the universe. It's everything is everything, blah 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 blah." And finally, I got to the point where like, okay, and then the math works. And
it does,
and it really is amazing stuff of the special and general relativity. And I did like I taught a course in high school in Canada, right? And even showed people how to derive equals MC squared. It's not mysterious and work.
It takes very little, actually.
Yeah.
You can get there in like a page and a half.
Yeah, and demonstrate stuff. But that was the process to try to give the students ideas, because I think they should teach relativity first, and then say a simplification of relativity will do this Newtonian mechanics because it's good enough for most things, right? But that's thing. So then
this may be off topic, but I've heard that relativity, the mathematics of relativity is in conflict with the math of quantum mechanics.
General relativity.
Well, in fact, actually not. It's the special relativity. Einstein dealt with flat space-time.
Yeah.
Space-time was not warped by gravity.
That works quite well with quantum mechanics.
Yeah, but the thing that happened, so then Feynman next thing was to say, okay, now that you understand relativity, let me introduce you to quantum mechanics. And he started talking about quantum mechanics, and I said, I'm only 17. I'm an arrogant SOB, and actually said to Feynman when he was talking about quantum mechanics and the electron goes through both slits at the same time, I said to him, "Now you're just being silly." Understand? Feynman would make deliberate mistakes on the blackboard, and if I didn't catch it, he'd get mad. So I just did a bunch of math that's garbage. You didn't catch it. You're not paying attention. Let's start again.
That's hilarious.
Right. So I said to Feynman that he's being silly about quantum mechanics, and so Feynman very very calmly said, "Well, why?" and explained how, from a purely relative standpoint, this quantum mechanics stuff was rubbish. And he laughed and said, "Yes, that's very good. Those are valid objections from that standpoint, but who's to say?" Right. And so, in fact, when we went off to college, his thing is like, okay, you have objection to quantum mechanics. I want you to do experiments. I want you to design an experiment to refute quantum mechanics. Catch it.
Yeah.
I spent a lot of time in college designing experiments to try to catch it, and guess what? I lost because both relativity and quantum mechanics are some of the most well confirmed to amazing precisions in all of physics, and yet the two don't play nice at the extremes. One of the extremes is perhaps the early state of the Big Bang process. Another is around the edge of black holes, other things. The two, we don't have
so general relativity is in conflict at those extremes.
Yes.
General relativity is in conflict with quantum mechanics,
and quantum mechanics is in conflict with general relativity too. Let's be fair to both sides. And so what it says is that our view of the universe is perhaps incomplete, and so people have been trying to explain gravity from a quantum field position. We've been unable to do that.
Like the standard model with the elementary particles, it doesn't include like the hypothetical gravitons, for example, right? Like there is no. It doesn't
That's
include.
who you asked.
Yeah.
But yes. So anyway, but this is beyond the. We've gone.
Sorry for sidetracking the conversation.
Yeah, we can get back to this.
More of the stuff in BE1.
Yeah, we can get back to this in the Q&A, but we have two more main topics to get through.
Yeah, and then I have two audio things I want to play.
Yeah, our penultimate topic is, what is cosmology?
Well, I should have been like the first one.
I can imagine in terms of stuff, in terms of when you're talking about physical cosmology, right? It's a branch of cosmology that really is about the understanding what the
branch of physics.
The cosmos is the universe, right? So it's the physics of the universe.
Yeah, I've heard some people say the universe is in the cosmos, and there could be multiple universes in the cosmos, and the cosmos is the bigger thing. I've heard people say that.
If the multiverse exists, it'd be part of cosmology. But if it doesn't exist, it's not part of cosmology. Cosmology is about the
I would say it's the study of the origins and history of the universe or multiverses, if multiverses are already.
And structure.
Right? Cosmology deals with how the universe came to being, what its structure is, what it is now, how it's evolving, and what will happen in the future. That's sort of what cosmology kind of deals with. Yeah.
I've asked this question. I think I asked questions earlier, but as someone who studies, you probably don't have as much argument as they do as biologists do with creationists. But do creationists argue with you about the subject?
I mean, it used to be that Earth creationists were madder at the biologists than the astronomers, right? They didn't really understand what we were doing in astronomy. And it was kind of nice because we kind of didn't have to deal with as many sort of nutcase stuff. But I'm sorry, but some of the people in that area are really nutcases, in my opinion. So yeah, it's a problem now that people are kind of realizing that if you want to have the universe be some number of thousands years old, cosmology has, you have a lot of problems with cosmology as a result of that. So, what's our next topic? Maybe you should move on. And I have some audio, so I want to have commentary on.
And the final topic of the night is
the universe infinite or finite? Answer is we don't know. There are Big Bang model interpretations that suggest the Big Bang process created infinite space and time. There's other topologies of the universe that are finite, right? You can have, it's like a ring, right? You can go around in a circle and don't reach the edge, right? You can have things that have a fixed finite size but have no boundaries. We know that our visible universe horizon is finite because the Big Bang process has been going on for roughly 13.8 billion years. So the longest a photon could have traveled as a result of the Big Bang process and things that happen is 13.8 billion years. And that turns to about a distance around 68 billion light years, but that's kind of a horizon. And over time, that horizon expands. But that's kind of we don't know. There is nothing in the Big Bang models that say it must be finite or it must be infinite. If people ask, is the Big Bang expanding into what? And the answer is, well, you could have, in the infinite universe, it doesn't expand anything. It just gets bigger.
Yeah.
You double the number. What do they double into? Numbers.
Yeah.
Right? It's not that number.
Like you mentioned, previously you mentioned about dark energy. Like that most of the universe is, or at least most of the energy total of the universe is mostly dark energy. You have also something called dark matter and ordinary matter. And if I think also one of the notes that Vandalia included in the document, it mentions that like if you have a certain amount, if you count up all of the ordinary matter, the dark matter, and dark energy, it has just enough energy for the universe to remain nearly flat, or maybe perfectly flat.
That parallel line stays straight and it doesn't move around.
Yes.
We don't see it warping back to itself. We don't see the back of our heads if we keep looking long enough. That's it seems to be flat there. So in the universe, when we talk about energy, because E equals mc squared, matter, energy, we talk about universe as energy. Today, about 72% of the universe is involved in this acceleration of the universe, this what we call dark energy. Bad term for it, but it's the stuff that's causing the grid of space to expand. 70% of the energy of the universe is dark energy. There's another 23% that is involved with what we call excess gravitational fields. Now, people think those gravitational fields are a result of matter, but we can't see or detect that matter, so we call it dark matter. So 23% is involved in this excess gravitational fields. At least 4.6% for all the rest of the normal stuff. So all the particle zoo stuff we're doing, hydrogen physics and the standard model and protons and atoms and neutrinos and photons and all that sort of stuff, black holes, all that stuff it's really only about 4.6% of the energy of the universe. And we found that there is this 20% of excess gravitational field, which we think might be a result of mass or might be that gravity's different. And 70% is accelerating the universe, which is we call dark energy.
So would finite mean that the universe would there's a boundary to the universe that will make it stop expanding,
or the universe curves in on itself. So maybe the space, right?
It could be periodic.
Like on a ring, you come back to your spot. Obviously, it would take a long time. So by the time you come back to where you were, it's different, right? But the geometry of space doesn't have to be infinite. It could be curved in on itself, as an example.
Like a map in a video game where if like Asteroids, the game Asteroids.
Or Pac-Man, yeah.
yeah. Where so Asteroids would be a two-dimensional version of a finite universe without a boundary.
Yeah. So at this point, I would like to do two things. Play a 4-minute audio set. We'll stop by a really great astronomer called Phil, who goes by the name of Bad Astronomer.
And if anybody wants to listen to these uninterrupted, the links are down in the description below at the bottom of the description section. You can listen to them without our commentary.
So we're going to have about a 4-minute thing. We're going to stop and talk about some of the things that are there. But I like one of the way that Phil does. This will help reinforce things. So without further ado, let's get it started.
Very common misconception that the Big Bang was an explosion in space with everything rushing away from some point. But that's not what's really happening. Remember, I've talked about space being a thing in which matter and energy exist. Space can be warped or bent by mass, creating what we think of as gravity.
By the way, that's what I just said, that's basically Einstein's general and special relativity theory, but mostly general relativity, right? That of matter and space being kind of intertwined, being warped.
Talk about the universe expanding. We mean space itself is expanding. And when it does, it carries galaxies along with it. In a sense, it's...
So again, if galaxies, if ignoring the fact they might be orbiting each other, you know, the center of mass of a cluster of galaxies is really kind of staying put, unless something is pushing it, like another cluster, you know, like it's being attracted away. But they're mostly staying put, and it's this grid of space that's expanding. All right. So we're now going to analogy.
Having a rubber ruler. When you pull on it, it gets longer, and the distance between the tick marks gets wider. When the ruler doubles in length, the tick marks that started out 1 millimeter apart are now 2 millimeters apart. But tick marks that were 10 centimeters apart are now 20 centimeters apart. In other words, the farther away a tick mark is, the faster it appears to move away. So
this is the Hubble limitory expansion law, right? That says the farther out you go, the faster those things are generally receding away from you, ignoring local variation.
It scales basically. Like at the 10 times greater distance, it's the expansion rate is 10 times greater even. Yeah.
Yes.
Yeah.
Now we learned later that scaling is not linear, but it's accelerating the dark energy thing. But that's a different story. So
it's not constant over time, is what he means by not linear. Not that it change. Yeah.
No, with distance, not, but with time, it is changing. Yeah, with time. Yeah.
So let's go going on.
Apart. In other words, the farther away a tick mark is, the faster it appears to move away. Sound familiar? That's just what galaxy redshifts are telling us. It also means that really the galaxies aren't actually doing any moving. It's that space between them is expanding. This may seem like a nitpicky semantic point, but it's physically true. The galaxies are, for all intents and purposes, standing still. The space in between them is where all the action is.
And so that's where we talk about expansion of the universe and why, you know, the Earth-Sun distance is not changing, why the Milky Way galaxy is expanding. In these local regions, gravity is strong enough to bind things together that they got to stay put. You know, they might orbit each other.
So I guess it's also true that space within my own body is also expanding, but because the distance is very small, you don't notice, you cannot notice the expansion rate.
The banding, but I mean, I would say in the distance, on the other hand, I would say it differently, that within your body, the chemical bonds and structures are holding you together, right?
Yes.
And that the expansion of space is not sufficient to cause your body to expand, right? The bonding, the binding energies of stuff hold you together, just like the gravitational forces on the Earth hold stuff to the Earth. Sorry, flat Earth people, and that the distance of the Earth-Sun system is also gravitationally bound. You know, due to
but even if the atoms in my own body were not bound together, the expansion rate would still be very unnoticeable.
Yeah,
but you would also be dead.
And so
exactly right. Yeah.
Islands of stuff hold together against the current inflation. So it's saying the action is actually really between superclusters of galaxies. But
I guess we're lucky that the continents don't move as fast as the universe is expanding.
Yeah. So you're not going to see and be able to see expansion at the local scale. It's at the cosmological scales, and that's what he says where the action is. So let's continue on here.
It's even weirder. This is true no matter where you are in the universe. From any galaxy, it looks like all the others are rushing away from you. Look back at that ruler. No matter what tick mark you start with, when the ruler stretches from that spot, it looks like the tick marks are all moving away from you. This is what Einstein's equations showed and what Lemaitre saw in them. Space is expanding.
And so this is one of the things about the misconceptions. There isn't an origin of the Big Bang. Everything is expanding away from everything, even though there are local spots that other forces that keep it together. right?
So where do you get this rubber rule? Where do you get these rubber rulers at?
Well, I don't know. It would be obviously maybe the two you want to have in your channel in your store is rubber rulers that people can use to stretch. Normally, a rubber ruler is not very effective, but
yeah, they didn't have those for stuff in elementary school.
But yes, I think you should find a store for rubber rulers and put it into your store.
Yeah, if anybody out there wants to make me a tucking time with Kathy rubber ruler,
yeah,
feel free to create one for me.
Okay, we have a few more minutes of this thing, and then we're going to another.
The Big Bang wasn't an explosion in some pre-existing space. It was the initial exploding expansion of space itself. The universe isn't expanding into anything because it's all there is.
That's an important point. And people sometimes misconception about the Big Bang. The big expansion of space isn't expanding into something. It is the something that's expanding. I know it sounds semantical, but that's a very important point.
So it's true. So is it the case that a model of the universe where, maybe for another several radii compared to our observable universe, it's sort of the same, but then it does drop off to sort of zero mass density? Is that consistent at all with, or is that contraindicated?
It is consistent, but again, beyond the observable universe, we can't observe, right? It is, but we don't have any reason to think that beyond our visible horizon is anything different.
Yeah. Okay.
So I guess the question that I could ask is like obviously we know that the universe, the space is expanding, but of course we tend to think about space like a nothing basically, but this implies that space is a something. But what is being produced that causes this to expand? Like, is there something popping in that makes the space expand, or like I don't know what terms you would have to use to describe more space, basically.
Well, if the universe were infinite, there's nothing to expand into. It just gets bigger. Just like the number line is infinite, and if you double the numbers, you still have an infinite line, right? An infinite universe that expands is still infinite. It doesn't expand anything. If it's finite and closes in on itself, it could be that the ring, let's say if it's kind of like cylindrical, just gets bigger. It doesn't expand anything. It just gets bigger. And it's hard because it's counterintuitive. But
the amount of space, like I don't know if it's the correct terminology to use, but the amount of there's more space being produced, basically.
Yeah.
Or
I like to say that the graph paper. If you have graph paper, people are just adding more lines and stretching it, right? The dots on the graph paper, where your universe expand, just like the dots on a balloon, get bigger.
Of course, when you stretch something, you don't produce more stuff, basically, right? But in space, you are producing more space.
And the steady state model has been refuted. That was their excuse as well. There's matter being created spontaneously that keeps the universe there, but we know now that's been refuted by observation. So let's go back to what he's saying here. Few more minutes.
The universe isn't expanding into anything because it's all there is. There's nothing outside the universe for it to expand into. This also means the universe has no center, no point of origin. Imagine the ruler is now a circle and the diameter is expanding. No tick mark is the actual center, yet no matter where you are on the ruler, every tick mark appears to move away from you.
So this would be an example of a topology that of a finite universe that's closed in on itself as opposed to infinite, right? And we don't have an experiment right now to suggest one or the other. It appears to be flat and appears to not favor a universe curved in on itself. If it is, it's much bigger than our visible horizon.
Like if the universe were to turn into itself, it would basically be a 4-dimensional sphere, right? Like instead of a 2D surface on a sphere, you have a 3D surface on a 4D sphere. Almost.
Yeah, that'd be an example. Yeah. Space-time, depending on how dimensions you add to space, how many dimensions you add to time, that dimensions of space-time is really what would be folding in on itself. But so these analogies about rulers and balloons and so forth are to give you sort of they're not real. They're just give you inclinations of what the math suggests, which may be correct or maybe incorrect, because the universe doesn't have to ask your permission to do what it does, and your math may be wrong, right? But here so far, it's pretty good. Let's go finish on this thing before we're going to do one on.
Similar way, every spot in the universe appears like the center, which means none is. No place in the universe is more special than any place else. We're all in this together.
So, and that's a very Einsteinian relativistic thing, that there's no special spot, right?
So you're saying the Earth is the center of everything. Earth is everything reflects the Earth, revolves around the Earth. Is that what you're saying?
Well, if you were a different spot in the universe,
it's true.
The same thing happening, right? And everything is receding away from you. Everything is receding away from everything.
I guess it's like standing on planet Earth and you see like, oh, I see the horizon is surrounding me equally distant in all directions, but no matter where you are on the surface of the Earth, you see the exact same thing. The horizon appears to be equally distant around you, basically.
Yeah. So last thing is just a few moments from a thing from Dr. Tyson, Neil deGrasse Tyson, people know. He's having a conversation with Chuck Nice. And they're talking about.
I don't think I've ever heard of that guy. Is he someone important? Is he someone famous or important?
I mean, he's a co-host of the Star Talk. Star Talk is a show that deGrasse Tyson does to have interviews and explain things.
Well, whoever this guy is, I hope he does something important with his life.
Yeah,
whoever he may be.
He is actually Chuck Nice is a comic. He provides comic relief, but he's also incredibly smart, right? He tries to play the foil on there and make jokes, but he actually knows a lot of stuff. He's a really smart guy and quite impressive. So let me and we'll talk about what so this particular thing. We just had a press. We had press releases where someone says, "Oh, Big Bang proven wrong," blah blah blah, or that the James Webb Telescope involves Big Bang, and Neil is basically putting that in perspective. So let's hear what Neil has to say.
So here's the point: the tenets of the Big Bang, that the universe started out small, hot, dense. Where matter and energy were a primordial soup, where the forces of nature had merged. All of that is thoroughly supported by observations of this universe.
I'm going to say, this is not wild speculation, right? We have observations and hard data to back up the model, which is why you can elevate it to a theory. And we'll talk about this some more in BE1, but this Big Bang process is not like, oh, they're just speculating, right? There is hard science evidence that backs up stuff. Let's continue.
Thoroughly supported. Okay, now there's some things that, well, did this really cause that, or might it be something that we don't know about yet? And who ordered up the dark matter? We don't know where that came from. And where's this expansion? We don't know where that came from, but we can describe it and we can measure it. Here's the point. If tomorrow you have a new idea about how the universe works, it's going to enclose everything we've been talking about up to that moment that has been experimentally and observationally verified. You could.
So this is one of the things where some of the things that Penrose kind of goes off on tangents, right? We know, we observe, we measure a bunch of stuff, right? And if you come up and say, no, I think the universe came out of the nose of the great turtle, like Terry Pratchett type things, that would have to explain everything we know and observe, right? it's more likely if we're going to refine the Big Bang model and have new theories, or even theories about the cause of the Big Bang process, or even maybe trying to explain multiverse over, you'd have to start with what we know now and observe now. It'll be expanding on the Big Bang model concept with refinements, not refutation and replacement. Let's go on just with a few more.
It in something deeper. Okay, you can say, well, I have an idea. Our universe is just one in a multiverse. Right. Fine. Okay. But our universe would have started with a Big Bang. Okay. And our universe would have expanded from a dense, hot, cool state that has been cooling ever since. That's observed and that's real. And that's not going away.
Okay. So again, this is not idle speculation. This is based on hard data that has been built up over the years.
That's my point. So what you have are journalists trying to make clickbait. And if there's some little thing in the early universe that is still on the frontier, still being contested in the octagon, in the fight dome, and some new idea is emerging over another idea, people say, oh, Big Bang is in trouble. Scientists go back to the drawing board. But Big Bang is not in trouble. Right. I'm just saying, it's not in trouble. It is a whole thing that could conceivably fit in a deeper, bigger idea. Right. But it's not going to be swapped out tomorrow. We're not going to find out tomorrow, gee, the early universe was cold instead of hot. That is not going to happen.
So again, data, they're not, he's being definitive. I would say, I don't know if this would allow that to happen, because you'd have to explain the data and then explain why it was started off cold rather than hot, right? That's a wait a second. So I want to just add those two things together in a perspective to wrap up some of the stuff there. I guess, are there any questions from the chat?
Yeah.
No, our lovely panel here.
Yeah. So if you have any questions for Landon or any of our guests, put them in chat now or forever hold your peace until a month from now.
Well, I had one question saved up for now. Like, if you go again back to the moment when before, at the moment all the hydrogen and helium was in a plasma. The electrons freely moved around, and photons were they bounced back and forth between electrons because the universe was opaque. But at some point, they have a recombination. The atoms become neutral, and then the photons were free to move. And those photons we see today as the cosmic microwave background radiation.
Yeah. And in fact, those photons, we call them cosmic background. They were the last bounce off of plasma, right? As a plasma was cooling in different, and not all simultaneously, because the universe was not a perfectly equalized thing. It had lumps and cosmic spots, but that when the photons were bouncing around, and in the last bounce of plasma before it went neutral, the photons just go free off there, and we see them as this microwave glow.
Yeah, it was qualitatively actually a similar-ish environment, I think, to the photosphere of the sun.
Yeah. And
I think, like, even in terms of density, I don't think it's like crazy different than that.
Yeah.
And it's basically the temperature when hydrogen and helium become a gas instead of a plasma.
That also depends on density and stuff. It's actually not the ionization temperature. If you just look at like the Boltzmann factors, you actually need like 100,000 Kelvin. But that's because the statistical mechanics are more complicated.
And that's the thing. So I remember, and I was in the audience when the cosmic background data was presented, right? And we were all waiting for this thing, the first reveal, right? And I remember it was
Kobe.
They were sitting in the audience, and they showed the graph, and they said, "Well, here is the black body curve." When you see this sort of statistical Boltzmann-like thing, it's like a bell curve that's lumped on one side, right?
Yeah, it's just a boring line.
And so the line, and they said, here is what the cosmic electron measured on intensity and frequency, and you saw the same curve, and it was like, okay, black body, that was a good round of applause. And then they said, here are the error bars, and like,
and then they didn't show anything.
No, if you zoom down, the error bars are so small that they're with less than 1 pixel. Right? It was like and that was when thundering applause and
yeah.
This was the now definitive thing that this background is black body. The temperature is there. Not only that, that we're dealing with a universe which the visible horizon was 1,100 times smaller. The frequency was 1,100 times higher. The temperature was higher. In fact, the temperature it corresponds to when you measure it back is the ionization temperature. How much energy it takes to take a boundary electron and
like at that like if you go back at that moment when when recombination happened, the universe was still pretty hot. Instead of a black background, the universe would have been bright orange in the background, basically.
Now we're going to talk about this in BE2, not BE1. We're about in BE2 because there's weird stuff that happens even earlier in the Big Bang process. Because
my question was about at the time the background radiation was like bright orange, and over time it got red shifted towards the microwave spectrum. But my question was like these photons have lost energy during that time, and my thinking is energy cannot be created nor destroyed. So where did the energy go during the redshift?
No, the frequency.
That's my question.
The frequency of photons have changed, right? The energy density is now over a larger volume because of the expansion of space. So the average density is there, and so this redshift is not a loss of energy. It's a stretching of stuff. It's a consequence of the fact that the photons have to go at C unless they're interacting with stuff. So because of that, because of the way like expansion, you get a change in energy per photon. So the density has dropped, right? Remember, you start off with hot, dense stuff that was actually so interacting that it was relatively uniform, and it became lumpy.
So basically, the energy of those photons transmitted to the energy of the space, or not? Like maybe I'm misunderstanding.
That and also on these scales, on cosmological scales, it's not clear that conservation of mass energy holds in the same way as it does. Conservation of mass energy it can be derived from an assumption about physics being invariant as time changes, and that doesn't seem to necessarily be the case on cosmological scales. So you don't actually necessarily expect conservation of energy. It's very weird.
Yes.
We have 3 questions from our viewers. The first question from Jacob is, it says, "Are magnetars?"
Yes, they are.
They're favorite stars.
My favorite stars.
So magnetars are stellar remnants of highly magnetic stellar remnants, right? And we'll talk about this, I think, in BE3 when we're talking about how stars evolve, and some of the things that the collapsed stars can basically concentrate the magnetic field, so you get enormously strong magnetic fields, just unimaginably super strong magnetic fields, and weird stuff happens as a result of those very, 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 very intense magnetic fields.
I believe the magnetic fields are so strong that even the magnetism alone would kill you, basically, right?
Yeah. Like electrons stop noticing the nearby proton because they're just getting ripped by Lorentz forces or something.
And its gradients are just wacky to the thing. And so when we're talking about in I think it's BE3, we're talking about stellar evolution and supernovae and so forth. We're going to get with you think things are bizarre. Wait until you get to some of that stuff. But good point. So what's the next question?
Magnetars are also a type of neutron stars, right?
Yes.
Yeah. All right. Okay. Sorry for the interruption.
No.
Tina wants to know about the expansion.
About the expansion.
She says you mentioned the expansion wasn't linear. I'm trying to wrap my head around that. Not sure how. From the question though, does that mean expansion fits and bursts?
So let's go back to that ruler, rubber ruler analogy, right? If I am doubling the ruler every minute, that would be a linear expansion. If I'm accelerating the stretching of the ruler, that's the acceleration of space. And that push is what we think dark energy is involved in, right? So not only Hubble showed that the ruler was expanding, right? Getting farther away, go faster. But what we've learned from people, Reese and I think it's in 2011. Nobel Prize was awarded for accelerating the universe, that the expansion of the universe is getting faster, right? So it's expanding, but it's expanding faster. So that rubber ruler is expanding, but it's going faster and faster and faster, right? And then about 5 billion years ago, gravity was enough to try to keep things together, and it lost. And now dark energy has got the upper hand, and so the universe is accelerating. It's getting the grid of space is getting bigger faster.
So I guess you can graph the expansion of the universe as an S curve. Like first, the curve went concave down.
Like
Yes, like that. And then at 5 billion years, it went concave up.
Yes. So if you look at his nice little chart there, he's done. Very nice for us. And you look at the line at the very beginning, right? Maybe you can expand it and stuff. If you look at the very beginning of the line, and you drew a slope, you would get to a date which is well, if you did the other way, you go from today, go backwards from today, you would end up hitting the intercept at a different spot, right? So if you go from today, which is up on the line, and go down, you would end up
this is today. This is now. And this is our idea, an assumption. We haven't measured this part, right? But we do measure that it's starting to curve up.
Well, I would say, based on that data, we have 5 billion years of curving up a little bit.
Okay, yeah. So I meant to put it here then.
So if you draw the line, you're going to intercept to an earlier date.
Okay, yeah.
And so this is where early on with the Big Bang
model,
we measured the expansion of nearby stuff, because that's kind of what we could do at that time. And at an age of 10 to 11 billion years, which we knew was in trouble because we had things older than that. Now, because of that little S-curve thing there.
Yeah.
Now, in addition to that, so we're seeing the intercepts. So that's where we had things. It's being nonlinear there, and the other thing that happens is way down close to that origin.
Mm-hmm.
Other weird stuff happens, but we'll talk about that in BE1.
Yeah.
And I'm not talking about monetary inflation. I'm talking about real.
And the final question that we have so far before we end is
no.
Could we turn Venus into a black hole for science without messing up the solar system? Well, I don't know how you would class Venus, where you get the energy to do it.
The mass would be the same,
Venus
right?
turned into a spot that was, I think, on the order of like a millimeter or less. The gravitational field to be so intense that you'd have a black hole in horizon. The rest of the solar system would keep going around, right? We wouldn't. Black
The
holes
mass
don't.
would be the same, right? The mass would be the same.
Yeah. It just like say if you took the sun and collapsed it into a black hole, we'd still orbit the sun just fine, right?
I want to say a word in defense of Venus here. Okay, turning a planet into a black hole is messing up the solar system. Okay, that's messing up the solar system.
It messes up Venus, yeah.
Black holes are not these cosmic background things. We wouldn't be sucked into the sun.
Yes,
if the sun
it would behave
turns
gravitationally the same.
Our models of stellar evolution is that the sun doesn't have enough mass to turn into a black hole. It'll turn into a white dwarf, just a little cinder thing. But big stars that that form black holes, things that orbit beyond 3 times the event horizon radius can orbit just fine, unless they're knocked into it. That's a different story.
So we go on. Do any of you have any advertisements for stuff you're doing coming up?
I am supposed to be appearing on Professor Park's PhD's show tomorrow morning, I think.
You want to link that in the? You want to link?
I don't even know if I don't even have a link for it right now because I'm bad at life. And then I have Bad Science Sunday tomorrow night with Maya. I can drop a link to that. Well, I can drop a link to the.
You said the power to have links. I think I made you a moderator last time you were on.
Yeah. I put the thing in the thing.
Right.
So yeah, we just hit 500 subscribers. So
yay! Congratulations. Subscribe, by the way. Go ahead.
Yeah.
It costs you nothing. It gives him everything. So So
yeah.
free. Do it.
Subscribe, the thumb up, bell if you want to, and share, of course.
Yeah.
Landon, anything coming up for you?
So you're talking about for me?
Yeah. Anything?
Yeah, a couple of things. On January 27th at 13:30 Pacific, that's 1:30 p.m. Pacific. I'm on Chester's channel called Unnamed Tavern, which will be politics and things of that nature. On February 2nd, we have the Volcano Show, where we talk about the Kilo volcano in Hawaii and volcanoes in general, what's happening. That's going to be on February 2nd at 1 p.m. Pacific. I also run a Discord server called Our Favorite Universe. Hopefully
link to that. The link to that in the description below too.
That link will work for 7 days, starting on the 20th. If you link and I see you join there, then I'll elevate you to a science fan. In that thing, the primary thing is the science channel of science articles that go up. There's also a thing about cooking and eating. There's about history, about medical stuff, disasters, and current news, and so forth. So there's a bunch of things going on there that I would invite you to check out. And of course, I'm involved with the International Obfuscated Seed Code Contest, trying to get that stuff started or restarted. It's the internet's oldest contest about programming in C. And finally, I'm working with people to help to establish a telescope on the South Pole of the Moon, hopefully by Artemis 7 in the future.
Okay. Ness, anything coming up for you? Any appearance on the channel coming up?
Personally, on my own channel, I'm not active, but I'm more active on Jackson Wheat's channel. Like I'm a video editor of his, so my work goes mainly through his channel. So if you want to know more, go check out Jackson Wheat.
As for me, if you want to, we will be continuing this mini series in a month's time, the 3rd Saturday of February. So I can't remember the exact date of that, but 3rd Saturdays, look it up. But if you want, but for more recent history, this coming Thursday, we'll be talking about the reign of Julius Caesar.
Yes, interesting dude. Of course, I hold the Senate of Rome in high contempt. They're one of the worst legislative bodies in history, and they're quite disgusting. And Julius Caesar and some of the other things that came about was because of the Senate of Rome, which was a bunch of people that I think deserve condemnation, not praise.
Yeah. Same with Julius Caesar.
and they made, because they were such lazy asses, they made Julius Caesar a god and basically said, "You do the thing," and because we don't have to do anything because we don't have to be responsible. So.
And before we end it, do any of you have any catchphrases you like to say at the end of your streams?
Well, I want everyone to again enjoy wherever, whether it's morning, noon, or night, depending on your time zone and latitude. And I hope you continue to enjoy our favorite universe.
Join my cult.
Like and subscribe.
Yeah, you all of us stay before after we end it off stream, but for the rest of you, never stop learning and enjoy the randomness. We'll see you all next time.
Yay.
Bye.
Bye.